Hi, I'm Ethan Kwan, and today I'm going to be showing you our beautiful Earth getting destroyed by Sirius B. And Sirius B is a white dwarf that is basically in the main system called Sirius, and this is just a hypothetical example, but after Sirius, I don't know why it's called Sirius, destroys Earth, sadly, I'm going to be showing you a real-world example, a real-world example where basically this is happening. Not exactly Earth being ripped apart by Sirius. As you can see, it's already being ripped apart. It's already being ripped apart here. Sorry. The atmosphere disappeared. Anyway, it's lagging a lot. But this is actually happening in real life. Not with Earth and Sirius B, but with a different system called SAX J1808.4-3658. Where a pulsar, a vastly spinning neutron star, I don't know what's happening here, a fast spinning neutron star is ripping apart a brown dwarf. And it looks like Sirius B is orbiting Earth for some reason. Anyway, let's just get started. Alright, so now we have basically what we want. We have a brown dwarf, as you can see right here, that is orbiting a pulsar named J1808.4-3658. Now, the official name is this, but I'm gonna call it I'm gonna call it Rippy from now on. So Rippy is a binary system where a brown dwarf orbits a pulsar. This is a pulsar. This is a rapidly spinning neutron star. I guess I should quickly explain what's the history of a pulsar and how pulsars form and how they form. Yeah. So a pulsar is a rapidly spinning neutron star. This time I turned it down, like the rotational speed, so it doesn't lag that much, but normally it's a few times every second, and the most fast spinning pulsar, known as a millisecond pulsar, is spinning at, well, as the name suggests, every, like, a 1,000 times every second. Wow, that's a lot. Anyway, how pulsars form. A pulsar is a rapidly spinning neutron star, like I said. A neutron star is formed when a star about 1.45 masses of the sun and higher explodes as a supernova. A supernova is a how huge stars like higher than 2 masses of the sun die when they die. And what is left behind is their core. Their core is a neutron star. All right? Okay, so this is not exactly the right explanation. If you want to put in a better explanation, why don't you put it in the comments below? Anyway, this is basically the system we want. So we have this system. Now I'm going to play it. And as you can see right away, the brown dwarf gets super hot because, well, since it's so close to a star, yeah, it's getting hotter, and it's actually starting to get ripped apart. That's what we want. This pulsar, about 11,000 light years away, is ripping apart a brown dwarf. Kind of sad. Don't do that. And it's forming a ring around the pulsar. So it is losing a lot of mass very quickly, as you can see here, and it is going toward the pulsar and basically orbiting it, like as you can see here. and some of it escapes into outer space, some of it lands on the pulsar, but most of the time it just orbits. Sometimes the disk becomes unstable here. Here, the disk here becomes unstable. When that happens, the disk will actually start to, well, this stuff right here is hydrogen. The hydrogen, whoa, that means it's really hot. The hydrogen is gonna be, when the disk becomes unstable, the hydrogen is gonna be funneled into the pulsar by its super strong magnetic field. When that happens, when it lands on the pulsar, it will undergo fusion because it's so hot there. When it does, it will basically fuse into helium, and it will land on the pulsar. When this happens, and then it's pretty cool. Well, first of all, let's cool this down because I don't want it lagging that much. What's the highest? Whoa, that's a lot. -270. Much better. Nope, not anymore. Anyway, yeah, it's kind of impossible to cool down because, well, there's a lot of material flying around, so it will collide with the brown dwarf, adding mass to it. Also, one of the reasons is because, well, it's super close to this star here. We can check the proximity to its host. If we see, it would be in motion, wouldn't it? Motion, and then it would, that's actually pretty close. Let's see in AUs. Yeah, not even like 10,000th, no, 1,000th of the distance between Earth and the Sun. That's very small. Or we can get it in kilometers, or Earths. Let's see, Earths. Yeah, around 26 radii of the Earths, and that's really close. Well, astronomically, it's really close. But yeah, this is what's happening. Then after the conditions are fine, right? When the conditions are just right, this high helium that's piling on the pulsar will expand in a very powerful blast. Well, not that powerful, pretty powerful. So here we can simulate that by, I'm sorry, I'm gonna explode. Where'd it explode? There it is. I'm sorry. So we're going to explode the pulsar. Now this is not what happens. The helium explodes, not the actual pulsar, but we can simulate that. Or can we? I don't think so. So, and we get a supernova. I should have expected that. But anyway, the helium blows off in a spectacular, awesome. Doesn't have an orbital parent, no, right? But it does come out in a fireball. The hydrogen dissipates into outer space, and the helium comes out and then settles back on the surface. This was over in 20 seconds. And this is actually happening. On August 21st, 2019, the NICER telescope on the ISS... Wait, what? NICER telescope on the ISS basically captured this happening. Yeah, so... Brown dwarf, will you come out or something? Anyway, yeah, so we have... This is kind of what's happening in space right now. By the way, a brown dwarf, if you're wondering, a brown dwarf, well, a star forms when particles come together in a whirlpool. We can simulate this by putting a planet down and then shooting hydrogen at it, because that's how it formed. That's how it formed. We're gonna shoot hydrogen at it. And if we do that, we'll get a shower of hydrogen. Oh, it's paused, that's why. Never mind. Anyway, kind of. That didn't work, did it? Let's try again. Yeah. Doesn't seem like it's working. I'm gonna have to add this manually. So, go to composition, add some hydrogen. Okay, so as the hydrogen goes up, it will expand, and why is it so hot? Anyway, oh, that's why. Okay, never mind. Well, then I'm gonna have to do this with Jupiter or something. So Jupiter. Okay, Jupiter is considered a planet, right? But once anything gets above, well, let's see. We are going to put in mass, for mass, I'm going to put Jupiters. So it's going to be one Jupiter. Now what we're going to do is we're going to shoot hydrogen at it. And we are going to make them pretty big, because we don't want it to like be super slow. I'm going to put it in Earths. I'm going to put how about 0.5 Earths each particle, or maybe 0.01 Earth. Okay, so let's watch it go up. Okay, so it is going. Yeah, it's definitely going. Remember, each particle is 0.01 Earth. That's pretty big. Anyway, let's keep going. I'll tell you when it becomes a star. Hopefully it will. Okay, so it's at 1.16 Jupiter, so it's going to take a while. So I am going to raise it to maybe 1 E plus 24. That's maybe around the mass of the moon. Yeah, around the moon. Yeah, no, a little bit bigger than the moon. But it is going to be better. Watch this. Yeah, much faster. But this is how stars form anyway. Okay, fine, I'll narrate while this is happening. Okay. So, this is how stars form. This is how normal stars form. Now, if it's bigger than 11 Jupiters about, the mass, like right now, this is considered technically a brown dwarf, because it's bigger than a planet. The biggest planet is 11 Jupiters, and it's smaller than a star, which is about 80 Jupiters. Well, the definition of a star is when it's able to do nuclear fusion because of heat, but still, it will depend on its mass. So first of all, I'm gonna add some more mass. So I'm gonna do, maybe 0.1 every time. It should go up super fast now. Watch. Oh no. Okay, it's getting close to the definition of a planet. So I'm gonna put 0.001. Okay, so the definition, well, this is still technically considered a planet, well, a brown dwarf, sorry. But right now it's getting so heavy that it might as well be considered a planet. Well, I'm going to add it manually. So let's see. There we go. Yep, so here, so around 79 masses of, yeah. So we have successfully created a star. That's not really we wanted to do that, but it's not really what we wanted to do. Yeah. Anyway, yeah, that's cool. So that is how brown dwarfs form. They are considered failed stars because they failed. They couldn't get enough mass to form a star. So anyway, that's all for today. Thank you for watching. This is going to be awesome. Maybe I should collide something with this because it's fun. What? Anyway, see you at howtodotutorials.com, and see you next time.